To understand the composition of the universe, astrophysicists rely on a standard theoretical framework known as the lambda cold dark matter model, or lambda CDM. This chart shows the standard cosmic inventory dictated by that model. It partitions the universe into three isolated components: baryonic matter, which is the normal atom-based matter we can see, dark matter, and dark energy. Theoretical physicist P.J.E. Peebles helped build this foundational framework. It strictly treats these elements as distinct self-gravitating components that interact but remain separate entities. But treating them as separate pieces creates severe observational friction. For decades, researchers have searched for isolated non-baryonic dark matter particles, like WIMPs or axions, which are hypothetical elementary particles. Yet physical detection continues to turn up empty. There is corresponding theoretical friction on the other side of the chart. Dark energy is not mathematically defined as a static cosmological constant, represented by lambda. A static constant representing uniform vacuum energy fails to explain the dynamic, accelerating reality of cosmic expansion. Modern cosmology remains partitioned, treating deeply interconnected astrophysical phenomena as isolated, disparate mysteries. Researcher Sasikala Jagadeesan argues that the dark sector components are not distinct particles at all. Instead, they are varying kinetic states of a single continuous field. To frame this, the research utilizes an Eastern philosophical matrix, specifically Vethathiri Maharishi's concept of Sudhaveli, or absolute space. The core axiom of Sudhaveli is that space is not an empty container. It is an active, self-compressing fluid that shapes and moves continuously. Jagadeesan's methodology takes established, peer-reviewed astrophysical observations and maps them directly onto this philosophical matrix to resolve the conceptual fragmentation of the field. Translating Peebles' lambda CDM framework through the lens of a self-compressive vacuum provides a consistent, unified physical model for the universe. This animation shows the modern quantum mechanical understanding of the vacuum. The quantum vacuum, the lowest possible energy state of a field, is not actually empty space. It is filled with continuous energy density and pressure fluctuations. Recent peer-reviewed research by scientists V.G. Georgiev and A. Mater suggests these localized vacuum fluctuations scale up to drive massive, large-scale cosmic movements. This physical mechanism maps to the traditional Sudhaveli definition of space. Space acts as an active and pressurized plenum rather than a passive void. The vocabulary differs. Physicists call it quantum field fluctuations, while the philosophical framework calls it self-compressive active space. Both disciplines describe a similar physical baseline. Reality is built on an active, pressurized field, not empty nothingness. We see the effects of this pressurized field in galaxy rotation curves. Outer galactic arms spin so fast they should tear apart, so the standard model requires invisible, non-baryonic dark matter to account for the necessary gravitational pull keeping them together. Albert Einstein redefined gravity to eliminate the idea of an invisible pulling force. He showed gravity is the geometric curvature of spacetime itself. This diagram shows the synthesis of these mechanics. Dark matter is interpreted here not as an undiscovered particle, but as the localized surrounding pressure force of the spatial vacuum. The self-compressive nature of the space field pushes inward on baryonic structures. This external pressure accounts for the mathematical effects currently attributed to excess internal mass. This pressure-based interpretation aligns with alternative physics models like MOND, modified Newtonian dynamics, which adjusts gravitational rules at low accelerations, and emergent gravity. In this view, gravity and dark matter are identical phenomena operating at different scales. Both represent the inward compressive pressure of the self-gravitating space field. Standard cosmology assigns structural stability to the dark matter halo, a theoretical region of invisible mass extending far beyond the visible galaxy, to prevent it from fragmenting. Mapped to the unified Sudhaveli model, the halo represents the physical limit of the vacuum's compressive capability. The inward energy locks into a geometric equilibrium at this boundary. It stabilizes, preventing the surrounding pressure from causing further collapse into the galactic center. The dark matter halo acts as the stable, quantum geometric boundary condition of localized space compression. That leaves dark energy, the mechanism driving the accelerated expansion of the universe. The DESI collaboration, the Dark Energy Spectroscopic Instrument, recently published observational data indicating dark energy is not a static cosmological constant, but a dynamic, evolving field. This dynamic data matches the Sasikala concept of expansive waves. These waves are generated at the extreme limits of structural compression and rotation. When compressive vacuum energy reaches its maximum density and rotational spin, fluid mechanics suggests it must emit a repulsive outward force. This mechanical interpretation aligns with the dynamic nature of the DESI data, suggesting that dark energy is a direct expression of the field's kinetic state. Dark energy shifts from an unexplained repulsive force into the necessary outward kinetic counterpart to the universe's inward self-compression. This table compares the partitioned lambda CDM model on the left to the unified continuum of the self-compressive field on the right. Standard gravity and dark matter are viewed here as expressions of the unified field's localized inward surrounding pressure. The dark matter halo marks the geometric equilibrium limit of that inward compression. Dark energy functions as the dynamic, outward expansive wave generated by the rotational friction of those compressed nodes. The entire dark sector can be modeled as dynamical expressions of a single continuous field, rather than disconnected parts. Modern mathematical cosmology and traditional philosophical metaphysics appear to be converging on the same fundamental behavior of the spatial vacuum. While the search for isolated dark particles has yet to yield a physical detection, recent observational data points toward a continuous, self-compressing energetic fluid system. By prioritizing the fluid dynamics of space over the hunt for individual particles, future astrophysical simulations can model the cosmos as a continuous, interconnected system. Reconciling these models suggests that understanding the universe requires looking past the fragmented pieces and recognizing the pressure of absolute space.